We're getting into an example 3 now, and this is our large example, our large demonstration that we're going to be going through. And we're going to do 1 acre of plant production, or right abouts there, okay? So we're going to use gutter-connected greenhouses, again, sticking with a standard 30 by 96. But these will be gutter connect, so instead of coming down and having sidewalls that go to the ground, they come down and then they go right back up to the next greenhouse. So they're all connected into one large square structure. But this is going to be 15 bays of gutter connected greenhouse, giving us a total of 43,200 square feet of plant growing area within these greenhouses. We're going to do lettuce production for a wholesale market. We're going to do a decoupled design. We're going to grow rainbow trout along with lettuce. The rainbow trout will be in a decoupled building. The lettuce will be in this gutter-connected greenhouse. We're going to utilize pure oxygen, or not pure, but we're going to use oxygenation through oxygen generator and space cones. That's how we're going to deliver oxygen to the system. And the fish building will be constructed for the RAS system. So we're not going to get into building construction design, but that is included in this project is we will build a separate building to house the RAS once we know the actual footprint it's going to take up. Okay, so first let's lay out the growing area in the greenhouse. We know the sizes. We've actually, in the last example, we laid out a really efficient layout inside of a 30 by 96 greenhouse. So we're going to actually use the same layout for plant troughs. We're going to put 2 12-foot by 86-foot long plant troughs in each bay of the 15 bay greenhouses. 15 structures times 2 troughs per structure gives us 30 troughs. We have 2,064 square feet total out of 2,880 square feet of growing space in that greenhouse is taken up by the plant trough space. And that's 72% of the footprint. Now, usually you want to use at least 80% to have an efficient greenhouse design, but within the rest of the space, we'll use that for building seedling systems, okay, for a harvesting area to actually harvest the crops. So we'll be above 72% of the footprint in total growing area per bay of the greenhouses. Okay, total plant growing space is 30,960 square feet. In this design, we're going to be pumping out roughly 17,400 heads of lettuce per week. Okay, so large scale, we're moving a lot of product, and you're not selling 17,500, 17,400 heads of lettuce locally per week. It's not going to happen unless you have a booming local market, okay? So this jumps us into the wholesale marketplace. We've got a total of 30,960 square feet, and though most lettuces are around a 1 plant factor, for a little bit of a safety factor in there, we're going to size our plant factor at 1.2 because we do have differences in the varieties of lettuces. And I would just feel safer having a little excess nutrients. If we needed to, we could always top off with fresh water. The other way, if you don't have enough nutrients, you have to go through adding fertilizer. So I'd rather be on this end of the spectrum. Okay, 37,152 grams of fish feed a day, which comes out to be 82 pounds of fish feed per day needed in nutrients as an average over the growth cycle for the rainbow trout. 82 pounds times, we're going to say a 1.3% body weight average. That's average what we're feeding to the different cohorts of trout, a little bit different than the tilapia. But that gives us the number of 63 times 100 equals 6,308 pounds of fish needed on average to eat the 82 pounds of feed per day that we need as a nutrient source for the plants. 6-month grow out from 30 grams to 500 grams harvest size for rainbow trout, okay? And we're going to use the information established from an FAO manual, and you can find that online. Just Google FAO manual rainbow trout. That'll pop right up. But that's where this chart comes from, and it gives us from 0 weeks to 16 weeks of growth. We've got the growth on the bottom, horizontal axis, on the vertical axis, we have their average weight in grams, okay? From 30 grams to 500 grams is our growth cycle. So we're going to start basically get fingerlings here. We're going to grow to here, to a harvest plate size rainbow trout. So that chart is where I'm deriving these following numbers from. So from the FAO manual on rainbow trout, I calculated that if we're using a 4-tank layout and growing the fish for 6 months, that's the period from a 30-gram fingerling to a 500-gram adult, then the tank 1 population is going to be 53% of the total fish population. Tank 2 will be 27%, tank 3 will be 14%, and tank 4, our smallest tank, will be only 6% of the total population. So this is fairly different than the tilapia. Tilapia, we're at 42% in our heaviest tank. In this scenario, with rainbow trout, 53% of their weight is in that heaviest tank. And what that means is they grow less uniform than the tilapia. They're growing very fast in this last 6-week period here. They almost double their size, okay? So that's a little bit different scenario because some fish grow differently. So for rainbow trout, these are the numbers that I calculated from that manual that are going to be in the populations in our different tanks. Now, we want to increase the size of our maximum feeding rate and thus the maximum stocking density by 33.2% from our initial calculated feed volume to achieve that as an average over the 6-month growing period in a 4-tank system, okay? Just like we did for the tilapia, I figured out that percentage that we need to increase by so that we maintain that number as an average over the whole growing period, the feed volume, and not as a feed volume the day before our final harvest when all the tanks are at their heaviest. So this is the magic number for the rainbow trout, and it was calculated very easily off of that chart that we saw on the slide before, okay? So if we multiply 33.2% times our 82 pounds of feed, we get 27 pounds of feed. Add that back to the 82 pounds, and now we get our true maximum feed rate that we need to design around. And that's 109 pounds of feed per day. That relates back to fish at the 1.3% feeding rate per day. And it gives us 8,385 pounds of fish at a max. So we're already getting real hard numbers that we can design around. And I hope you understand where they're all coming from, because we've done this a couple times before now. And I hope you're starting to get the trick of it, get the hang of it. Okay, so 8,385 pounds of fish at our max density. And since we know the percentages in each of those culture tanks, we just multiply 53% times this, and we get 4,444. That's our max density in any tank, because that's our heaviest tank. Then we do that by 27%, we get 2,264. This times 14%, 1,170, and times 6%, 503. We add all these up, we're going to get 8,385 pounds. And that's the layout of the tanks. At maximum density, when we're ready to harvest this tank, this is how full they are going to be. Now, how full are they going to be when we harvest this tank? So this is erased, okay? This is your heaviest tank, next heaviest, and we're going to restock with fingerlings, okay? So your lightest tank is going to be restocked with fingerlings. Well, we have to figure out how many fish this actually is. And from the chart, since we said we're harvesting at 500 grams, we would divide 4,444 pounds by 5,000 grams, and that gives me how many fish we actually pulled out of this tank. Then we multiply that number by 30 grams, which is how big they are when we're restocking them into the system, and that gives us the weight for this tank, the lightest tank, after we've harvested, okay? 30 grams, which is the stocking weight of our fingerlings, times the amount of fish that we're actually stocking into the system, okay? Fairly easy. So we've established that 4,444 pounds is our max stocking density, eating roughly 53 pounds a day in that tank. Using oxygen, the experienced operator can achieve densities of 1 pound per gallon. For this example, we will use 4 5,000-gallon culture tanks with a max density of 0.88 pounds per gallon so that we don't have to move the fish during the grow-out period. So we're going to keep the culture tanks all one size so we don't actually have to move the fish, but we are going to use pure oxygen to size the oxygen requirements, and we're going to bring the density up to 0.88 pounds per gallon, which is far above the 1/4 pound per gallon that we have been designing for in our previous 2 exercises. So this is an extremely dense grow out, not as dense as we can possibly get it, so there is a little bit of safety factor in there, but this is going to be a lot of fish in that water volume, okay? We're going to use a Cornell dual drain design. Because we're utilizing pure oxygen, we can more efficiently collect and remove those solids through a center bottom drain where we send part of the flow, we send the rest of the flow out of a sidewall skimmer box, as we've talked about in that part of the lesson. So we've established we have 109 pounds total feed per day. We have 53 pounds of that food is going into our heaviest tank full of fish at our maximum feeding time. Because this is a full recycle system, we want to size the oxygen requirements at 1 pound of oxygen per pound of feed, or 1 kilogram per kilogram of feed. And that means that 109 pounds of feed per day, we're going to need 109 pounds of oxygen per day supplied to those fish tanks. Okay, it's 53 pounds of oxygen per day required by the heaviest tank of fish on the day of harvest. So for this example, we're not going to design every tank to require 53 pounds of oxygen at the same time. We're going to only supply our oxygen, size our oxygen supply for the maximum amount needed at all 4 tanks in one time. So that will leave us with a more realistic oxygen volume need. The fish require a max of 53 pounds of oxygen per day, and that's at 83 gallons per minute flow rate, which if we were to turn that tank over 1 time per hour, that's nowhere near enough oxygen. Okay, we would have negative 35 DO at the outlet before we inject any oxygen in the tank. So that right there tells us we would have to achieve a very high oxygen saturation level to get where we want if we are going to be at negative 35 before adding any oxygen to the tank. So if we increase this to 400 gallons per minute, okay, and this might take you doing a couple calculations, slowly increasing it to see where the numbers fit. At 400 gallons per minute, the calculations after the mass balance that we did in week 2 show that the water leaving that culture tank will leave at negative, if it's coming in at 10 milligrams per liter, it's going to leave at negative 4.16 milligrams per liter before we inject oxygen. But that is actually something we can work with, okay? We can work with this. If we want to maintain a minimum of 6 milligrams per liter leaving the tank, okay? So nowhere in the culture tank is it going to be less than 6 milligrams per liter, then, and we have a 400 gallon per minute flow rate, and we're feeding 52 pounds of feed per day, we need to inject oxygen at 20.16 milligrams of DO, milligrams per liter of dissolved oxygen. All right? So when we inject at 20.16, we're going to use all the oxygen that we've supplied, and the water will leave at 6 milligrams per liter. And that's directly off of the calculations that we learned in week 2. Okay, so instead of coming in at 10 and leaving at negative 4, we're coming in at 20 and we're leaving at 6. Does that make sense? So we're actually, which we could not achieve that with normal aeration, right? Because we can't get above 8 to 10 milligrams per liter. But with oxygen, we can saturate the water above that. So that's what we're going to design around. We just sized the flow rate, the oxygen requirements for the largest tank in the system. Now, go back and solve for the other 3 culture tanks at their maximum densities, okay? I want you to solve the water flow rate and the oxygen requirement for the other 3 tanks. Since we are using the same size culture tanks, they're all 5,000 gallons, we can estimate the required flow rates in the other culture tanks as a percentage of our now known flow rate requirement for tank 1. But it's important to note, because the fish eat a different percentage of body weight throughout their life cycle, and then our biggest tank, we calculated it off of what they are eating in that tank, these numbers are going to change a little bit, okay? And because of that, we want to go back and do the long math like I just told you to do in the slide before. For hard calculations, do the long math. For this, quickly, I just ran them as a percentage so we can get through this example a little quicker. All right, so tank 1, 53% of the fish mass. We have a flow rate of 400 gallons a minute to achieve 6 milligrams per liter oxygen when we inject at 20.16 milligrams per liter at the inlet. Well, in tank 2, since this is 53%, well, if this is 27%, that drops the flow rate needed to 204 gallons per minute to achieve 6 milligrams per liter at 20.16 milligrams per liter injected at the inlet. So because we have less fish mass, we don't have to inject the water as quickly with the same amount of oxygen in the water, okay? Tank 3, same thing. The flow rate that we need to inject at the same amount of oxygen is 106 gallons per minute. And tank 4, the flow rate is 45 gallons per minute. Now, adjust for percentages of body weight per day eaten of the different cohorts. That's basically the adjustment you need to do. So these are close numbers, but if you do the long math, you're going to get a harder number for each tank, okay? And the other way you can look at this is, if you didn't want to inject 20.16 milligrams per liter at the inlet and you wanted to inject less in this tank for some reason, you can increase the flow rate and inject less oxygen. So if you really want to change this around, you could definitely do it by keeping all the flow rates higher and lowering the oxygen going into each one. There's a lot of different ways you could do this, but quick and easy, this is how you could size the flow rate and the oxygen concentration for each of these tanks. So we know we need 1 pound of oxygen per pound of feed. We've established that it's a fully recirculating system, and that is right out of the yellow book. This is the amount of oxygen we're going to need. 109 pounds of feed going in, and that's also 109 pounds of oxygen per day. 4.54 pounds of oxygen per hour is our requirement, okay? So that divided by 24. Now we can size our oxygen generator off of this requirement. We know we need 4.54 pounds of oxygen per hour. So size the oxygen generator off of that. When you go to buy an oxygen generator, they'll sell them pounds per hour of oxygen. Very easy. And you can buy either a positive suction or a vacuum type oxygen generator. Size 1 species cone for each culture tank off of the max oxygen injection rate, which is 53% of the max density of our fish weight, which is 2.4 pounds of oxygen per hour. So on each of these 4 tanks, we want to size a species cone that will handle up to 2.4 pounds of oxygen per hour. All right, and that will saturate our maximum amount of oxygen into the vessel. The required water flow through the culture tank may be more than the required water flow through the correctly sized species cone needed to dissolve the needed amount of oxygen into the water. Okay, so our calculation is telling us we need 400 gallons per minute going through that culture tank. Well, the species cone, to dissolve the needed amount of oxygen we have, it might not need 400 gallons per minute. It might need 200, something like that. So this is something we need to look at. If this is the case, we use multiple water pumps pulling water from the sump. Okay, one is our main recirculation pump, and one pump pulls from the sump, goes through our species cone, saturates oxygen, and is delivered to the fish culture tank. So there's one pump from the sump to the species cone, and there's one pump from the sump to the culture tank. Oxygen lines should be injected either as a separate line low into the water column so that it's not right by the top and you don't get all your high oxygen water near the surface where it might come out and to transfuse into the air around, okay? So you want to inject it low into the culture tank. Or that line can be plumbed in with the main recirculation line and mixed within the outlet manifold and delivered into the tank within one outlet manifold, okay? It can be mixed into that main line. In this example, we will assume the flow rates calculated in the previous slide are correct, okay? Because I didn't go through and do the long math on all the other smaller size tanks. So we're just going to assume those percentages are correct. But for the 5th time, I'll tell you, go back and do the hard math on each of those tanks because the numbers will differ slightly. 755 gallons per minute is our total required water flow rate in the recirculating aquaculture system for tank circulation and for oxygenation, which is our limiting factor. For something this scale, we will use a dual drain tank, like I mentioned before. And for this design, specifically, we're going to send 85% of the flow through the sidewall box and 15% of the water flow through the center bottom drain. And remember, this can be 10 to 20%, and this can be 80 to 90%. But for this design, this is the criteria I'm laying out. The bottom drain will go directly to a radial flow settler, where it will concentrate the solids in the fish tank. All the solids are still going to go out of that center bottom drain, even though only 15% of the water flow is exiting through that hole. The sidewall skimmer box and drain line will join the radial flow settler drain line and be sent to a rotary drum filter. Okay? So after your bottom drain line goes through the radial flow settler and pulls out up to 50%, maybe 70% of the solids, depending on conditions, that water line is going to join the water line that just came out of the sidewall of your tank that has 85% of your flow, and all that water, 100% of your water flow, will go to the rotary drum filter. Total water flow rate is 755 gallons per minute. Total waste per day is 109 pounds of feed times 25% solids. We have high levels of filtration. We're going to get a lot of solids quickly removed from the water column. So unlike 15% on maybe a smaller application where solids have a longer residual time in the water, this application, 25% are going to be pulled out of the water. Okay? That equals 27.25 pounds of solids per day. Flow rate through the radial flow settler at 15% total flow is 113.25 gallons per minute. We multiply that by 5 for a 5-minute retention time, and we get 566 gallons for a radial flow settler, and that's per tank. Okay, so we'll have 4 radial flow settlers, 1 per tank. The rotary drum filter will be sized off of the flow rate, 755 gallons per minute, and the screen size that you choose to use. Sometimes the manufacturer will also want to know total suspended solids removed daily, okay, which we can calculate off of our total feed input. I suggest sizing the drum filter with a 90 micron screen, as research has shown that it has not shown a significant difference in the total suspended solids removed when using finer micron mesh such as 60 or 30 micron. So the lower the micron number, the finer the mesh. And what this is basically saying is there's been tests performed, and when we use a 90 micron mesh, and we also use 60 and 30 finer meshes, we actually don't see much of a difference in the total suspended solids in that water column. And using a finer mesh will waste a lot more water. It's going to clog the screen more often, and you're going to have backwash cycles happening more frequently. So I would suggest 90 microns. The finer the mesh, the more water removed daily. You just said that. If your plants are using more water than the RAS is providing, you may opt for a finer mesh screen in the rotary drum filter to deliver more water to the hydroponic side just automatically through that filtration function. Or you can remove the extra water as needed from the sump in the RAS. A quick look at the Hydrotech sizing charts. If you Google Hydrotech drum filters and look at their sizing chart, just a quick look shows you that we need their Hydrotech model 802, which has a max flow rate of 888 gallons per minute in a cold water recirculating aquaculture system using a 90 micron screen. So they have already done a lot of the work for you. It's really easy. Looked at a chart, picked it out, okay? And you could pay somebody else a couple $1,000s to do that. You can do it yourself. It's very easy. We could use the K1 quick sizing formula, but let's just say K1 media is not available, or you want to use a sand biofilter, okay? Some other type of media. We're going to size this off of the SSA, all right? Size the biofilter using the efficiency rate of 1 gram of ammonia removed per square meter of protected SSA per day. 0.0929 grams of total ammonia nitrogen per square foot per day. Okay, this is per square meter, 1 gram per square meter. This is 0.0929 grams per square foot. We're feeding a max of 109 pounds of feed per day to the system. The protein in that feed will be 42% for this example, because that's probably 42, maybe even a little higher is what we're going to feed to trout. The total ammonia nitrogen is 109 pounds times the protein content, 42%, times 0.092, and that gives us 4.21 pounds of tan per day. 4.21 times 454 grams per pound gives us 1,911 grams. So I just changed it from pounds to grams because we size our SSA off of grams, okay? Our media. So we have 1,911 grams of tan per day. 1,911 divided by 0.0929 gives us 20,570 square feet of SSA, of surface area on the media that we need to process it. And of course, if we're just using square meters instead of square feet, it's 1,911 square meters because it's 1 gram per square meter. Okay? So we have 20,570 square feet of SSA of media. So we need that many square feet of surface area of media for biofilm and bacteria to attach to process the ammonia. Well, for this example, then let's just say we choose a media that has 500 square feet of protected surface area per cubic feet of media. All right, that's what the specs, we're looking through 20 different types of media. We pick this one type of plastic media and it tells us, it gives us 500 square feet per cubic feet of media, okay? Well, we take our number, 20,570, we divide it by the 500, and it gives us 41 cubic feet of media required. So we just related the SSA to the media, and we can do that with any media at all. All we need to know is what's the SSA per cubic foot of media. And any biomedia out there will give you that information. That's how you size it. 41 cubic feet times 2 equals 82. We're sizing the tank here, okay? 82 times 7.48 gives us a 613 gallon tank to hold this media. This would take up half of that tank. 82 cubic feet times 5, so 5 times that volume, gives us 410 cubic feet per hour. 410 divided by 60 gives us 6.83 CFM of air needed in this biofilter. So we just size the whole biofilter in like 30 seconds. Pretty easy. Because of the density, we want to fit lids on the biofilters and vent the CO2 out of the building. We're above a ½ pound per gallon. We want to degas CO2 out of the building, okay? Size vent lines using the airflow calculations we have already discussed. So you have 6.83 CFM injected into the biofilter, right? Well, that's your airflow. So with the PVC line coming out of the top, going out of the building, that's your airflow that's going to be going through that line. So just size it appropriately so you don't have any major friction losses and you're not pressurizing that biofilter to try to get air out of it. It's not very hard, but that's how you do it. Now, degassing CO2. Again, for every 1 gram of oxygen consumed, 1.38 grams of carbon dioxide is produced. So our fish are consuming 49,486 grams of oxygen per day. Multiply that by 1.38, and they are producing 68 1,291 grams or 150 pounds of CO2 per day. That's the actual CO2 production coming out of the fish. Much will be off-gassed through the MBBR, but at this density we still need to include a degassing column in our design. Because we're above our half pound per gallon, to be safe we want to include a degassing column. Rainbow trout have a CO2 tolerance in the 9 to 30 milligrams per liter range. Tilapia can probably go up to 60, even higher, but trout are a little more susceptible to it. So we designed for 20 milligram per liter max concentration and purchase a counter-current degassing column from a manufacturer and install it after the biofilter. Because again, the CO2 is not just coming from the fish, it's coming from the bacteria that are doing nitrification process for us as well. Possibly attached to the sump or given its own small sump before the water flows to the main sump. Okay? So water goes through the mechanical filtration, through the biological filtration, and then normally to a sump. Well, in between biological and sump, we're going to stick this degassing column. So you could possibly, depending on the layout, have the water flow from the biofilter into the top of the degassing column, trickle through that and land in the sump, or you can actually build a small sump underneath the trickle filter, the degassing column, simply to catch the water from that, and then the water would be transferred to the sump from that small sump. So it would just be a small sump to catch the water if you didn't want to house this over the actual sump. Okay. Purchase that, from a manufacturer, install it. We just said that. Possibly attach to the sump, or give it its own sump before the water flows to the main sump. We just covered that. If making your own degassing column, remember that you need 1 square feet of surface area of packing column media per 35 gallons per minute of water flow. Okay, you want to design it with a 3 to 5 foot tall fall, so it's long enough for the CO2 to be stripped out of that water. And we want an air to water ratio of 5 to 1 to 10 to 1, which when you buy your media, it will tell you what the air to water ratio is using different medias for degassing applications. 755 gallons per minute is our total flow, divided by 35 gallons per minute gives us a 22 square foot of surface area that we need to degas this much CO2, the total CO2 amount. That's roughly 5 feet by 4.5 feet wide. So 5 feet long, 4.5 feet wide, and 5 feet tall. This dimension, 5 by 4.4, gives us the 22 square feet, and then we've got 5 feet of vertical fall. Okay? This could be smaller since we are degassing some through the MBBR, but how much? How much are we degassing? We'd have to actually look at some specific CO2 degassing studies from an MBBR maker, and then kind of estimate how much is being degassed through that process. If using a fluidized sand biofilter, which we don't talk about a ton in this because it's really used for a lot of large-scale operations, but it could very well be used in this application. And if we were using a fluidized sand biofilter, this would be the correct size needed, okay? Because we're going to need to degas directly after the fluidized beds biofilter, and we're not getting any degassing out of that biofilter like we do out of a MBBR. So 1 gallon of fluidized waste per 1 pound of fish feed. We're going to design the mineralization system now, all right? And we know that for every pound of food, we get about 1 gallon of fish waste. 109 pounds of fish feed per day gives us 109 gallons of fish waste per day, liquid fish waste. We want to multiply that volume by 40, and we get 4,360 gallons for a stage 1 mineralization tank. Okay, we're basically creating a wastewater treatment plant at this scale. That's what we're doing. Takes up a little bit more area. If you don't want to include mineralization tanks in your design, you don't have to, okay? That's something up to the designer. The fish production will be much higher in relation to the plant production if you negate the mineralization tank. But you already know that by now, okay? So we got 4,360 gallons of stage 1. If we size stage 2 M tank off of our total ammonia nitrogen requirements, multiply that 4,360 times 0.25, and we're going to get 1,090 gallon tank. We're going to fill that 50% full with K1 media. Okay, you could go as low as 1/6, but since we're using, basically we want to multiply it by the efficiency of waste we're removing. And since we're using high levels of filtration, we're removing roughly 25% of that solid mass, then we want to multiply it by 25%. If this was only removing 15% of the mineralization, we do times 15, okay? And that helps us size based on the ammonia coming into that tank. And then we size aeration requirements just like we have been. Very easy, 5 times the culture, or the vessel volume, so 5 times the biofilter volume, that 1,090 gallon tank. So 5 times that, and we convert it to CFM. That gives us our air volume. And again, because we're doing lettuce here, we're going to favor for the higher oxygen concentration in our stage 1 M tank and do all aerobic nitrification and aerobic mineralization. We don't need anaerobic properties to supply extra phosphorus, and break that down and supply it to our plants. What we need is the nitrogen. That's really what we want because we're growing leafy green vegetables. At this scale, we will install a second small rotary drum filter between stage 1 and stage 2 with the waste outlet draining back into stage 1 mineralization tank. Okay, so at this stage, that is not a huge cost to throw into the entire cost of the build. It might be a $3,000 or $4,000 drum filter, and we're talking about a $500,000 to $750,000 project. That's not a huge percentage of the cost, okay? So that would make sense in this scenario. If you don't want to use a drum filter, you can make a giant static screen, pump into that, and have a worker pull that and spray it out every day and put it back into stage 1 M tank. But in this design, we're going to put a rotary drum filter between those 2 stages. And again, all the waste collected goes right back into stage 1. We will install a K1 upflow filter sized off of the expected flow rate between stage 2 of the mineralization tank and our hydroponic component sump. Okay, so we've got 15 of these greenhouses. This line is going to flow out and split between those 15 greenhouses into a sump, the central circulating sump between those two deep water culture troughs. And we'll talk about the sump in a few more slides. But this is going to flow out. What I would suggest is just send it through one large K1 upflow before you split the flow and go to the 15 greenhouses. On the other side, you could have 15 small K1 upflow filters dedicated right there to each greenhouse and have the water flow through that before it enters the sump. And this is to polish any excess waste that was delivered to stage 2 and to polish any of the biofilm that comes off of the biomedia, because it's constantly creating new bacterial spots, and because of the abrasion in that biofilter, the second stage of mineralization, it's knocking off sloughs of old, dead, dying bacteria. So to catch those flocks, you use a K1 upflow filter. Okay. Something different than we're doing in some of the other designs is the K1 does not constantly have water flowing through it because it's not a recirculating design. So the K1 upflow should stay lightly aerated but not enough to tumble the media, because we don't have constant flow through the vessel and we don't want it to go anaerobic on us. So put a small air stone, I would size it at 1/4 the size of your normal size so that it doesn't tumble the media but it keeps it aerated, okay? And step 12, size the heat pump. So we plan to house the RAS in an environmentally controlled building. All right, you're going to build an insulated building around this fish system. And it's going to have a thermostat, and it has heating and cooling, and it can keep the temperature where you want it. But we still want to include a heat pump in the design to keep the water temperatures precisely where we want them. Let's plan on a delta T of 5 degrees Fahrenheit. We don't need a huge range to heat and cool, but we want to be able to bring the temperature 5 degrees difference from the ambient temperature. Total water volume of 22,000 gallons when we include in the filtration and everything else. 22,000 gallon delta T with a 5 degree delta T. We do 22,000 times 10 times 8.33 divided by 12,000 divided by 12 hours of pull down. And I believe that's less week 4 where we did equipment sizing. I give you the formula for sizing chillers. Okay, this gives us 6.36 horsepower needed for the heat pump. And again, a heat pump will chill or heat the water. So it does both. 6.36 horsepower. If you want to look at it in BTUs, it's 12,000 BTU per horsepower, which gives us 76,320 BTU. Now, if I look at a chart from Aqualogic, who is a large supplier of recirculating aquaculture heat pumps, okay, they supply this equipment. If we look at one of their charts, which I have in lesson 4, the closest they have is a 7.5 horsepower that's rated for a 5 degree drop up to 27,600 gallons. So because that's the closest, the next smaller unit I think is a 5 horsepower and it won't do the job. This one will. That's the right unit. We picked that. We just sized the heat pump for the recirculating aquaculture system. At this size, the condensing unit will be installed outside of the building and the heat exchanger will be installed inside of the facility. It's just like an air conditioning unit. You don't want to install the unit inside of your house, okay? It's installed outside because it expels air as hot air as it's running. And you don't want to expel hot air in the same area you're trying to cool. It doesn't make sense. Water pump will be specific to the heat pump, sized off of manufacturer specs. So the heat pump has its own water pump. Doesn't have to do with the other 2 water pumps that we're already using in this design. So it's got 3 water pumps in this design. The main recirculating water pump, our water pump for the oxygen requirements, and our water pump for the heat pump requirements. We're going to pull water from the sump near where the water's flowing into the sump from our biofilter, from our last stage, or from the degassing column, okay? And we're going to flow back to the sump near where the water pickup is for the recirculation pump. So if you have a rectangular sump, we're going to pull from here where the water's coming in from the filtration, and the water is pulling from here to go to the fish tanks, and we're going to put the water coming back in at the right temperature at that end. Now, the sump will stay fairly well mixed, but you want to do everything you can to not pull from the same spot that you're putting the water back into. Because it gives a little bit, it gives a false sense of what temperature the water actually is. Size pipes correctly according to the equipment layout you choose and the methods described throughout this course. Okay, we're on to plumbing, and it's, again, the plumbing's simple. We just have to lay it out and we have to draw it out. Decide where these components are going to sit so that you can walk through the facility easily, harvest fish easily. If you need to get a rolling cart through there to bring in bags of fish food, you need to be able to do that. A lot of facilities make aisles wide enough that they can bring a forklift in. You may decide to leave an aisle big enough that you can back a truck in there, load the rainbow trout right out of the fish tank into a truck, and the truck's going to leave your facility. This is up to you. But that's why I can't really tell you the layout and why I'm not going to draw out the entire plumbing schematic for these designs. Okay, it's just drawing it out. And remember to draw your different pipes in different colors. It helps. So sometimes your drain lines will be maybe in blue, and draw your supply lines in red. Some of these lines are going to overlap, which means you're going to have to install them at different depths. I know just in my operation here, in some areas I have 3 different pipes crossing each other, and they're all at different depths within the sand because they're buried. And you have to decide where they're going to be, okay? Size the outlet manifolds for the fish tanks, just like we've discussed. Some other items to wrap it up. We need to size the sump. We already know how to do that. We need to install dissolved oxygen monitor on each tank. This is a must. Okay, this is high density production using pure oxygen. You want an alarm system to let you know if oxygen levels drop, and you also want bottled oxygen that will be delivered to that tank in case oxygen levels drop and in case of an emergency. You do not have long to react when fish are at these kind of dense populations. Handheld DO meter is also a must to double check against the constant monitoring dissolved oxygen system. Install alarms for low dissolved oxygen, low water levels, etc., power outages. Look into possible addition of automatic feeders to feed every 2 hours, which is very practical and is something that is widely done when culturing rainbow trout in a recirculating aquaculture system indoors. Okay, you can feed them every 2 hours. Backup generator, backup oxygen tanks, and backup oxygen generator are a must. Okay, generator for electricity problems, backup oxygen tanks in case you need immediate oxygen delivery to solve an issue, and a backup oxygen generator in case you actually have an equipment malfunction. You could also not use an oxygen generator and talk to a liquid oxygen supply company, have them deliver and install an on-site liquid oxygen tank that has positive pressure, and you would pull directly from that. You would size that tank based off of your monthly oxygen needs, and it would be refilled just like a propane tank or a natural gas tank is refilled by a service company on a contract basis. Now we are choosing to use, we're going to size the hydroponic water pump. Okay, we're going to move over to the plant side. We just finished the fish side. We're choosing to use aeration in the deep water culture beds because of the warm imaginary climate, okay? And in a warmer climate, it can work real well to use aeration, and we can use that to evaporate some of that water out of the troughs, helping to get more humidity in the air, which is going to cause evaporative cooling in this theoretic hot environment. Not a hot, humid environment. Let's think Arizona, something like that. Yeah, we're growing rainbow trout in Arizona, and that's because we have an environmentally controlled building. We can grow whatever we want in there, and then we send the water out to the greenhouses, and guess what? Arizona is great for hydroponic lettuce production, okay? So we can imagine this is our climate. Well, in Arizona, we have low humidity, so any of that water we're evaporating out of the tanks is just going to add to the cooling effects in that greenhouse. It's going to go out of the center vent and ridges in the greenhouse there, okay? Though the aeration will mix the nutrients well within those troughs, we still want to circulate the water between those two hydroponic troughs. And I suggest installing a small sump, 100 gallons in size, level with both troughs, okay? Pump water at one turnover every 12 hours into trough 1. So we're pulling from the sump, pumping into trough 1, and let it drain from trough 1 to trough 2. So at the far end, we'll have them plumbed together underground. The pipe will go as trough 1 raises, water will drain into trough 2. Trough 2 will drain back through and then drain back into the sump. So this causes a circle. It causes the water to circulate between these two large troughs. Okay, the two troughs are 12 by 86 by 1. So if we want to get the water volume in those troughs, do 86 feet by 12 feet wide, and it's only 1 foot deep, so I left that part out. Then we multiply that by 7.48. Gives us 7,719, all right, gallons. We have two troughs, so it's 7,719 times 2. It gives us 15,439 gallons total. And then we add in the 100 gallons from the sump. We have 15,439 gallons divided by 12, because we want one turnover every 12 hours. And we get 1,287 gallon per hour water pump. So that's not a very big water pump for running an entire greenhouse. And it's pretty low wattage as well. If using a heat pump, which we will be in this application, the supply pump that runs the heat pump will be higher than that flow rate, okay? So it'll be more than enough to also act as a recirculating pump within the system. And you don't need to include a dedicated pump. So we don't need to size one off of one cycle per 12 hours, because the heat pump flow rate is going to be more than that, and that's what we'll use to recirculate the system, okay? So let's size the heat pump for a greenhouse. We got 15,539 gallons total, and let's say we have a delta T of 10 degrees Fahrenheit. After we use evaporative cooling and everything else we're using in the greenhouse, we still need to drop the water temperature up to 10 degrees, or maybe during the winter heat it up to 10 degrees. So we do 15,539 times 10 times 8.33. divided by 12,000 divided by 12 hours pull down, and that gives us 9 horsepower. 9 horsepower of heat pump, okay? So multiply that by 12,000 BTUs and we get a 108,000 BTUs. A 9 horsepower heat pump per greenhouse. We need 1 per greenhouse, okay? It sounds like a lot. It is a lot, but that is a very important control parameter to keep the water temperatures where you need them, all right? If you were using NFT systems, well, that'd be a lot smaller. It's nowhere near as much water volume, okay? So there's other factors that come into play, but in this design, we need 1 heat pump per greenhouse. Think of this as like a heater for your swimming pool. You know, if you have 15 swimming pools, you need 15 heaters for them. Size water pump according to the manufacturer's specifications, because they have a minimum and maximum flow rate to go through that heat pump. And as long as you're within that parameter, it will work correctly. You won't freeze up the unit or burn up the unit. And again, that's going to be much higher than the once per 12-hour calculation we did on the last slide as a minimum requirement. Size water pump, we just said that, and this will also serve as your recirculation pump. So some other items to wrap up in the greenhouse, okay? We need to size the greenhouse fans, which is easy. We need to size supplemental lighting depending on the location. You may be down South Florida and you might not need any supplemental lighting. Arizona might not need much supplemental lighting, okay? But if this was done in a northern climate, you can bet you're going to need supplemental lighting, and that's sized off of the needed par per day, and we already know how to do that, okay? Think about adding an extra bay onto the 15 bays, a last bay, as a packaging and processing house. It's going to be a lot of product, you know, 17,500 heads of lettuce per week. It's a lot of product. It's going to need some space. Look at the layout and see where you can add efficiency in the design. Once you have the components out, what's going to make it more workable every day when you're walking through there or your employees are walking through there? What's going to make it safer? These are things you need to think about. Make sure the workflow looks smooth in the layout of the design. Walk-in coolers sized to your estimated production. That's a must on this size of production, okay? My scale, where I'm at my farm, I get by without a walk-in cooler. We harvest the morning of. We do a lot of things that are hard and difficult, but our customers appreciate. You're not going to be able to harvest the morning of delivery of 17,500 heads of lettuce, okay? You need an appropriately sized walk-in cooler for how much product you have and how long you're actually going to be holding it for. A purging system for the fish, okay? Size of purging system, as we've talked about, standalone. I'm sure you could look up more information on a purging system, but basically a small RAS system that we're not feeding. We're just going to hold the fish there. And we're going to salt it to help stimulate their immune system. We're going to hatch eggs, so either build a hatchery for these trout, or we're going to buy fingerlings from a fingerling supplier. And that depends on where you're at and you know what's available. I'm going to source bulk fish feed, buy that in bulk, and maybe even leave an area in the RAS building for a silo to hold your bulk fish feed. That's something to think about. Source your packing material. You're going to pack all these heads of lettuce in. It might be going into clamshells. They might be going into waxed cardboard boxes. That's something you need to actually source. And marketing material. I hope you've thought about that by this point, okay? You need to market and you need to sell this stuff. You need to have stickers to go on your boxes, things that make people aware that this product's coming from your organization and it's superior to everything else out there. There are many ways to design aquaponic systems, okay? Little conclusion here. Many ways to design aquaponic systems depending on the end user's needs and their skill level. Economies of scale are realized as the operation size grows. Okay, things get cheaper. It costs the same amount of money to put a dissolved oxygen monitor on a 1,000 gallon tank as it does on a 30,000 gallon tank. Okay, same amount of money. One monitor per tank, one probe per tank. So as things get larger, the overall cost of production comes down. The most important factor in any design is making sure that it is capable of turning a profit. All right, we've talked about a lot of stuff from really low tech to really high tech. And the end result is it needs to make you money, or it needs to provide the food that you're trying to get out of the system you're creating, okay? If you're not doing this to make money, you're doing it to provide food for underprivileged or whatever the case may be. The end result has to be positive. We can go out and buy the Cadillac, the Rolls Royce of equipment, but if that means we're losing money every year, it doesn't make sense, okay? So choose the equipment appropriate to the design and make sure the cash is going to flow before you waste your money. This is a lot of money to get in. This size facility, again, we're approaching $1 million in something like this. That's a huge investment. Make sure you've done your research. Practice makes perfect. If you want to get good at designing and you want to feel confident in what you do, keep practicing. And it doesn't mean watching this video 100 times. It means taking these scenarios and plugging in your own numbers, your own production numbers. Switching the crops up from lettuce to tomatoes. How does everything change in the greenhouse? And all the feed rates change. The size of the equipment change. Switch fish species, okay? Do designs without mineralization tanks and then with mineralization tanks, and see what's the profit at the end. If you're selling a high value fish, you might be able to make a little more profit actually doing no mineralization tanks, less plants, and a larger volume of fish in ratio, because you're getting a high value for that crop. It's not most situations, but you don't know until you run these multitude of scenarios and put them all into a business plan and see which one's going to be the bright star, okay? And one will stand out. One will stand out far among the others. And that tells you this is the direction you need to go, and that's where you start heading for your future, okay? And last but not least, a big thank you, guys. I really hope you learned far more than you ever thought you were going to learn taking this course. I hope it's opened your eyes to a vast amount of possibilities that you can use to change your life, okay? You can use to go from this point forward and do something you want to do. Do something that you feel good about every day. And I really hope that's what the takeaway is from this. You're armed with the knowledge to change your life, okay? Thanks again. I really appreciate you taking this course. And like every other session, don't be shy. Any questions on these examples, shoot me a question for the question and answer session, and I'll be sure to cover it during this week's Q&A. Thanks again, guys. I hope you enjoyed the course, and I will see you around in the aquaponics world.